Hello and welcome to Investment Insight. Before we begin, make sure to subscribe and hit the like button. Now let's break down what's happening in the markets today in a clear and simple way.
Yeah, and today we're looking at something that's just, honestly, it's fascinating.
It really is. We've got tech billionaires pouring just unimaginable amounts of money into nuclear energy, right? And it's all to power their artificial intelligence dreams.
Exactly. But there is this massive multi-billion-dollar problem that's sort of hiding in plain sight.
Right, because they have the capital, they even have the raw uranium, but almost nobody in the Western Hemisphere actually knows how to bake that uranium into usable fuel or, forge the steel to hold it.
Yeah, the supply chain is completely broken.
So today, our mission for you, the listener, is to figure out why the real story of this whole nuclear renaissance, it isn't about building shiny new reactors, it's about mastering this intensely regulated, totally backed up supply chain.
And that is really the perfect place to start.
Yeah.
Because looking at recent analysis from 2025 and early 2026, the narrative around nuclear energy has completely flipped.
Oh, totally. For decades, if you brought up nuclear power, the conversation immediately went to, carbon neutrality, right? Climate goals.
Right. But according to the research data, nuclear energy is rapidly moving from just a catchy policy slogan to a really highly aggressive capital market theme.
Yeah, the driver isn't just green energy anymore.
No, not at all. The drivers are AI data centers, these massive semiconductor fabrication plants, and really the broad push for industrial reshoring under the current Trump administration.
Right, because the Trump administration is pushing hard to bring heavy manufacturing back to the U.S. And when you combine that with building these massive AI brains, they all require an astronomical amount of electricity.
Staggering amount, yeah.
I want to stop and just look at the unit economics of that for a second, because I think a lot of people, beginners looking at this market, they assume we could just power all these new factories and AI centers with solar panels and wind turbines.
Which is a huge misconception.
Exactly. Think of solar and wind power, relying on the wind to push a sailboat. It's
Right.
great when it's there, but it's totally unpredictable.
Yeah, and if you are running a multi-billion-dollar AI data center, you are running graphics processing units, GPUs, that cost tens of thousands of dollars each.
Right.
You absolutely cannot afford to have those machines sitting idle just because, a cloud passed over the sun or the wind died down.
Variable power completely destroys the unit economics of artificial intelligence. It's
Right.
like trying to run a 247 factory on a sailboat engine.
It absolutely destroys it. Tech companies need what the energy sector calls baseload power.
Baseload power, right.
Yeah, it's electricity that does not fluctuate. It's like the steady heartbeat of the power grid.
So when you combine the massive computational requirements of AI with the industrial demands of reshoring factories, it makes sense. The capital markets have suddenly realized that nuclear is really the only high-density, low-carbon engine capable of running 24/7 without interruption.
And the numbers completely back up that realization. So, according to data from the International Energy Agency, the IEA annual global nuclear investment has jumped almost 50% just since 2020.
Wow, 50%.
Yeah, we recently crossed the $60 billion mark in annual investment, and the projections show that hitting $70 billion by 2030.
That is massive. And the U.S. government is actively forcing the issue, too, right?
Oh, absolutely. Back in April 2026, the U.S. Department of Energy launched this program called UPRISE.
Okay.
And the explicit goal of UPRISE is to secure 5 gigawatts of additional nuclear power by 2029, specifically to feed this massive tech demand.
Okay, let's give the listener a mental anchor for that number because, 5 gigawatts sounds a bit abstract.
It does, yeah.
So 1 gigawatt is roughly enough electricity to power a mid-sized city of about, say, 750,000 homes.
Right.
So the DOE is essentially saying, we need enough new power for 5 entire cities, and we need it in the next 3 years.
Exactly. And the really fascinating part of that UPRISE program is that they aren't even talking about building new plants from scratch to get there.
Oh, really?
No, they want to restart dormant plants and just push existing ones to their absolute limit.
Which is the perfect segue into what we're calling the illusion of the quick fix. Because the immediate assumption from anyone watching this space is that with $60 billion a year and huge DOE targets and, Silicon Valley's bottomless pockets.
We should be seeing construction cranes over new nuclear sites in every single state.
Right. But if you look at these IEA numbers, honestly, it just does not add up.
It doesn't.
Looking at a recent visualization of this data, It shows over $300 billion has been invested globally in nuclear over the last 5 years. But actual physical capacity, the data shows it completely stalled.
Completely flatlined.
Yeah, by the end of 2025, total global nuclear capacity stayed perfectly flat at about 420 gigawatts. So, how do you pump $300 billion into an industry and get zero net new power on the grid? Is this money just disappearing into some bureaucratic black hole?
I mean, a lot of it is, but you also have to look at what that money is actually funding. That $300 billion is largely being absorbed by the staggering costs of just maintaining aging infrastructure, navigating decades-old regulatory frameworks, and safely decommissioning old plants.
Oh, wow. So just keeping the lights on with the old stuff.
Yeah, exactly. The reason the capacity stayed flat at 420 gigawatts is that the 3 gigawatts of new power that finally managed to come online globally was perfectly offset by 3 gigawatts of older reactors shutting down.
Let me guess, political phase-outs.
Exactly, primarily driven by political phase-outs in places like Belgium.
So all that capital expenditure is essentially just treading water. We are spending billions just to avoid going backward.
Pretty much. And when you look at where the new bills are actually breaking ground, I mean, the geopolitical reality is stark. Out of the 10 new construction starts globally in 2025, which represents about 12.2 gigawatts of future Power 9, those starts were in China and one was in Russia.
Wait, hold on. Not a single new construction start in the United States or Western Europe.
Not one in that 2025 data set.
That's crazy.
Yeah, the West is issuing permits, holding committee meetings, making grand announcements, but the East is actually pouring concrete.
Okay, let's unpack this contradiction because this is the primary bottleneck we promised to explore today. The U.S. is the biggest economy in the world. We are leading the AI revolution. And if you look at the commodities market, we're experiencing a massive boom in uranium mining.
Right, the mining side is booming.
Yeah, we fast-tracked projects like the Velvet Wood mine in Utah back in 2025. We are literally digging the raw material out of the ground at an accelerated pace. So if we have the money, the tech demand, and the raw uranium, why are we so paralyzed?
Because there is a fundamental misunderstanding of the nuclear fuel supply chain. You know, a lot of retail investors see the spot price of uranium going up and just assume the primary challenge is getting the radioactive rocks out of the dirt.
Sure, it seems logical.
But digging up rocks does not solve the problem. First of all, despite the new mines, the U.S. still imports roughly 98% of its uranium.
Wow, 98%.
Yeah. But the much bigger issue is what actually happens after the rock leaves the mine.
Okay, I like to think about it like agriculture. Mining raw uranium ore is exactly like harvesting raw wheat from a field. You can't just serve raw wheat on a dinner plate and expect someone to eat it, right?
Right, no one wants to eat raw wheat.
Exactly. You have to clean it, mill it into flour, add yeast, and bake it into bread. Mining is just the wheat field. The bottleneck isn't the field. The bottleneck is the bakery.
That analogy is so helpful. But we really need to look closely at the mechanics of this bakery to understand why it's such an impenetrable bottleneck.
Okay, lay it out for us.
The process is just a staggering feat of engineering. So you start with mining the raw ore. Then you refine that ore into a concentrated powder called yellow cake.
Okay, yellow cake, got it.
But you can't put powder into a reactor. So you have a conversion facility that turns that solid yellow cake into a highly toxic corrosive gas. It's called uranium hexafluoride, or UF6.
Wait, gas. Why do we need to turn solid uranium into a gas?
Because of the next step, which is enrichment. And this is the ultimate choke point of the global nuclear industry.
Ah, okay, the enrichment phase.
Yeah. Natural uranium consists mostly of an isotope called uranium-238, which doesn't fission easily. Only about 0.7% of it is uranium-235. And that's the isotope you actually need to power a reactor.
Just 0.7%? That is tiny.
Very tiny. So
Yeah.
to separate the two, you have to pump that UF6 gas into massive, towering centrifuges.
And because U-238 and U-235 are like almost identical in weight, separating them is insanely difficult. Right.
Incredibly difficult. You have to spin these centrifuges at supersonic speeds, literally mash speeds, thousands of times in a cascading sequence, just to shave off the infinitesimally lighter U-235 atoms.
Oh my gosh.
The precision required is flawless. If a centrifuge wobbles by a fraction of a millimeter at those speeds, it completely destroys itself.
Wow.
Yeah. And then after enrichment, it finally goes to fuel fabrication, where it's turned back into a solid, pressed into pellets, and loaded into fuel rods.
So that mechanical complexity perfectly explains the geopolitical nightmare we are currently in. Because according to recent analysis, Kazakhstan mines about 43% of the world's raw uranium. They have the biggest wheat fields, so to
Right,
speak.
right.
But the capability to actually enrich that uranium, to send those supersonic centrifuges, is concentrated in just 4 global suppliers. And historically, Russia has maintained a massive dominant grip on global enrichment capacity.
Which puts the United States in a severe bind.
Yeah, because didn't the U.S. government mandate a complete ban on Russian uranium imports by 2028?
They did. We are essentially cutting off our access to the largest, most established bakery in town before we have built a sufficient replacement.
Which explains the massive influx of capital we are seeing in this specific sector. Like, in January 2026, the U.S. Department of Energy announced $2.7 billion specifically earmarked for domestic enrichment capabilities.
Yeah, that was a huge move.
Yeah, they awarded major contracts to American Centrifuge, General Matter, and Orano. And private money is aggressively following suit. Urenco recently pulled in $5 billion, and several companies are drawing up plans for billion-dollar enrichment facilities in places like Kentucky and Tennessee.
The smart capital is absolutely moving away from the mines and directly into the enrichment facilities.
Right.
But here's the catch. Even with $5 billion in private capital and $2.7 billion in government grants, you cannot just stand up a supersonic centrifuge facility in 6 months.
Well, why not? I mean, if tech giants are willing to pay massive premiums for power, why can't we deregulate the enrichment process and let the free market build these facilities at lightning speed?
Because nuclear supply chains are intentionally slow and closed. They are engineered to be agonizingly difficult to enter.
Intentionally slow. Okay, explain that.
Well, in the tech world, if a supply chain fails or a software update has a bug, a company loses some money, maybe a stock dips.
Right.
In the nuclear industry, a failure isn't a temporary dip in revenue. It is a catastrophic event. It is a Chernobyl or a Fukushima.
Oh, yeah. That's a whole different level of risk.
Exactly. When a safety parameter is breached in this sector, it takes decades to regain public trust. So safety protocols are a massive non-negotiable wall.
And beyond just the basic mechanical safety, there is the global security dilemma, right? This feels incredibly relevant when we talk about the next generation of nuclear technology. Small modular reactors, or SMRs.
Very relevant, yeah.
Because everyone in the tech world loves the idea of SMRs. They are compact, theoretically cheaper, and they can be manufactured on an assembly line rather than built on site. But SMRs require a very specific, much denser type of fuel called HALEU, correct?
Yes. HALEU stands for high-assay low-enriched uranium.
Okay.
Traditional, large-scale nuclear reactors use fuel that is enriched to between 3 and 5%. It is very stable and relatively low risk from a weapons proliferation standpoint.
Right.
But because SMRs are small, they need a denser, more potent fuel to operate efficiently over a long period. Therefore, they require HALEU, which is enriched to between 5 and 20%.
Okay, let's upgrade our bakery analogy here for you listening, because this is where the geopolitical tension spikes. Think of a nuclear enrichment facility like a high-tech oil refinery.
Oh, that's a good comparison.
Yeah, refining crude oil into standard unleaded gasoline is great. It runs your car and powers the economy safely. But if you tweak the exact same refining process and keep processing that fluid, you aren't making unleaded gas anymore. You are making pure, highly volatile rocket fuel.
Exactly.
An HLEU sitting at up to 20% enrichment is uncomfortably close to becoming rocket fuel.
That is the exact security dilemma that keeps international regulators awake at night. The technological leap from enriching uranium to 20% for commercial SMRs to enriching it to 90% for weapons-grade material is alarmingly small.
Seriously, just a small leap.
Yeah. The centrifuges do the exact same thing, they just do it longer. To put this in perspective, just recently, in May 2026, Iran's parliament issued a formal warning stating that if provoked, they possess the capability to easily enrich their uranium up to 90%.
Wow. So because HLE is just one step away from weapons-grade material, you can't exactly just zone an enrichment plant in a suburban business park.
Exactly. Facilities that produce HALEU require an extreme, almost suffocating level of security, surveillance, and constant monitoring by the International Atomic Energy Agency.
Makes sense.
Every single ounce of gas must be tracked. This intense, necessary security requirement is the invisible friction actively slowing down the entire SMR revolution.
So Silicon Valley wants these small reactors tomorrow, but international law dictates that the fuel supply chain has to move at a crawl. Okay, so even if we completely solve the enrichment puzzle, right? even if we build the heavily guarded facilities and secure our HLEU fuel, we still can't just plug these AI data centers in because there is a second bottleneck.
Oh, yeah.
We literally do not have the metal to hold the fuel.
The physical component bottleneck.
Yeah.
The parts required to build a nuclear reactor are some of the most complex, heavily scrutinized pieces of machinery on the planet.
You can't just buy them on Amazon.
No, definitely not. You need massive reactor pressure vessels that weigh hundreds of tons, forged from absolutely flawless steel. You need specialized steam generators, incredibly heavy steel forgings, and nuclear-grade valves that can withstand extreme pressure, heat, and radiation for decades without degrading.
And it isn't just the raw materials either, it's the human capital. We are facing a severe shortage of nuclear-certified welders.
Oh, the labor shortage is real.
Yeah, you don't just hire a commercial pipe fitter to work on a reactor. A nuclear welder undergoes years of specific training to ensure that every single weld they make is X-ray perfect. Like a microscopic air bubble in a weld on a coolant pipe isn't just a maintenance issue, it's a critical safety failure.
And looking at the data, this physical bottleneck is precisely why the U.S. Department of Energy is currently considering billions of dollars in financing mechanisms just to help utility companies secure these long-lead parts years in advance.
Why do they need government financing just to order parts early?
Because of the timeline mismatch.
Okay.
In a normal construction project, you get your building permit, then you order your steel. In the nuclear industry, if you wait until the Nuclear Regulatory Commission gives you the final permit to order your giant steel reactor vessel, you will be waiting another 5 to 7 years just for a specialized foundry to forge that steel.
5 to 7 years just for the steel.
Yeah. The DOE realizes that utility companies cannot tie up billions of dollars in capital for 7 years while waiting for a piece of steel, so the government is stepping in to underwrite that risk.
Wow. And this physical constraint is also creating massive opportunities for specialized manufacturers. I mean, we are seeing activist investor funds like Anonym Capital aggressively pressuring companies like BWX Technologies to commercialize their SMR designs immediately.
Right, because the logic is very clear.
Yeah, BWXT actually owns the highly specialized manufacturing tools and the skilled labor force required to build these components. In a market where a dozen tech companies want a reactor but nobody has the tools to forge the parts, the true pricing power sits entirely with the manufacturers.
But here's the thing. Even if you possess the manufacturing capability, you still need a standardized blueprint. And this is where the West has historically just shot itself in the foot.
France's EDF is the ultimate cautionary tale here, right?
It is a really painful case study. France's EDF is supposed to be the undisputed crown jewel of Europe's nuclear ambitions. They have the pedigree, they have the backing.
Right.
But their Flamanville 3 reactor project in Normandy has faced catastrophic multi-year delays and crushing cost overruns. We are talking about a budget that ballooned from roughly 3 billion euros to over 13 billion euros.
Over 13 billion. What specifically went wrong? Was it just, bureaucratic red tape, or was it a mechanical failure?
It was a failure of standardization. For example, in 2014, regulators discovered that the massive forged steel vessel head and bottom, which was produced by a specialized foundry, had elevated concentrations of carbon.
Meaning the steel was brittle and could theoretically crack under extreme pressure?
Exactly. So the regulators forced them to implement massive testing and ultimately mandated that the vessel head be replaced after a certain period of operation.
Ouch.
Yeah, that single component anomaly cost them years and billions of dollars. And it highlights the broader problem.
Right.
If every single reactor built in the West is treated as a custom, bespoke science project, with designs constantly changing mid-construction to appease different local regulators, you can never achieve economies of scale.
Right, you need an assembly line like building Boeing or Airbus jets.
Exactly. But currently, the nuclear industry operates like a series of custom boutiques.
Okay, we have covered a massive amount of ground here. We started with AI demand, moved through the enrichment choke point, the security risks of HALEU, and the severe lack of forged steel and skilled welders. So if you are a listener trying to navigate this landscape, how do you synthesize this into a coherent strategy?
The core insight to distill from all this data is a really simple framework. Do not chase the flashy headlines.
Yeah, okay.
At the end of 2025, uranium prices spiked to $82 a pound, and retail investors blindly rushed into mining stocks. But as we have explored, the raw material is just the wheat field. It is not the choke point. The real winners in this economic shift are the owners of the bottlenecks.
Right. If you want to understand where the leverage is, look for the companies that own the bakery or the companies that own the oven.
Precisely. Let's break this down by timelines to give you a clear map.
Let's do it.
In the short term, meaning the next 1 to 3 months, this market is entirely driven by momentum and news headlines. You will see spikes based on DOE grant announcements, geopolitical tensions, and the revival of uranium futures contracts, which the Chicago Mercantile Exchange is actively trying to push right now.
Right, the CME. But a critical word of caution here. A news headline about a billion-dollar government grant does not translate to instant cash flow.
Not at all.
The market often prices in these grants immediately, completely ignoring the fact that it will take the company a decade to build the facility.
Exactly. Which brings us to the medium term, the next 6 to 18 months.
Okay, what happens there?
If tech companies need power right now, they cannot wait a decade for a new SMR. So where do they go?
That's a good question.
The medium term is arguably the safest, most logical bet. Look at the mechanics, not the builders. I am talking about the companies performing what the industry calls uprates.
Okay, define an uprate for the listener.
An uprate is when you take an existing, already licensed, already operating nuclear plant and you upgrade its internal components. So like swapping in a more efficient high-pressure turbine or better heat exchanger.
Oh, I see.
Yeah, by doing this, you can squeeze an extra 10 to 15% of power out of the exact same reactor.
That makes perfect sense. The facility already has its permits, it already has an armed security perimeter, and it is already plugged into the grid. You bypass the entire decade of red tape.
Exactly. These maintenance and engineering companies can deliver new gigawatts to AI data centers infinitely faster than a consortium trying to build a new plant from scratch.
And finally, the long-term view. Say, 3 to 10 years out.
That is when you look at the companies attempting to build the bakeries.
Enrichment companies.
Yes, the enrichment companies, the SMR developers who finally lock in a standardized design, and the heavy component manufacturers like BWXT.
Got it.
Yes, the strict regulations, the agonizingly slow security protocols, and the intense international monitoring are frustrating to watch. But for an observer or an investor, that regulatory nightmare is actually a massive economic moat.
An economic moat.
It is an impenetrable barrier to entry. Once an enrichment company or a specialized parts manufacturer clears those hurdles, gets their licenses, and begins operating, it is virtually impossible for a scrappy new startup to come in and disrupt them. The heavy regulation completely shields the incumbents.
This has been an absolutely fascinating breakdown. It fundamentally changes how you look at the energy landscape. It isn't just a story about digging up uranium. It's a story of atomic engineering, international security, and supply chain leverage.
It really is. And I will leave you with one final sort of provocative thought to ponder as you watch this sector evolve over the next few years.
All right, what is it?
The tech giants driving this AI boom, the massive companies in Silicon Valley, they're historically accustomed to solving their problems by simply throwing billions of dollars at them. In the software world, capital buys speed. You hire more coders, you buy more servers, and you launch.
Very true. Move fast and break things.
Right. But in the nuclear world, capital cannot buy a shortcut past the fundamental laws of physics. Money cannot bypass the supersonic engineering required for enrichment. It cannot rewrite nuclear safety regulations, and it certainly cannot override international security treaties aimed at stopping weapons proliferation.
Wow.
So what exactly happens to the explosive, fast-moving artificial intelligence revolution when Silicon Valley's deep, bottomless impatience inevitably collides head-on with the most heavily regulated, intentionally slow-moving supply chain on Earth?
That is a great question to leave on. Don't forget to subscribe and hit that like button.